In this episode, we take a common beginner assumption and replace it with a safer, more realistic one. Security requirements are not something you check once at the end, because systems do not stay still long enough for that to work. Even when a team believes it is building carefully, small changes accumulate, dependencies shift, and new features quietly alter data flows, permissions, and trust boundaries. If verification happens only as a final event, the system often reaches the finish line carrying hidden drift, meaning it no longer matches the security intent that was approved earlier. Continuous verification is the discipline of checking, repeatedly and intentionally, that the system still meets the security requirements that define acceptable operation. This is not about paranoia or endless testing. It is about keeping confidence aligned with reality as the system evolves. By learning how continuous verification fits into modern delivery, you gain a mental model that makes many exam scenarios easier, because you will recognize when the real problem is missing feedback and evidence. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A solid place to begin is to clarify what verification means in plain language, because it is often mixed up with general testing or with compliance paperwork. Verification is the act of checking that what you built matches what was required, which includes security requirements such as access control rules, data handling constraints, auditability expectations, and availability protections. The reason this matters is that security requirements are promises, and a promise without verification is just a hopeful statement. Verification does not require deep tools or command work in your mind. It requires disciplined thinking about what evidence would show the requirement is met. Beginners sometimes assume that if a feature works, the security requirement must also be satisfied. But security requirements often involve properties that are not visible in normal use, like whether unauthorized access is blocked consistently or whether sensitive actions are recorded in a meaningful way. Verification is the bridge that turns a requirement into a provable claim. When you treat verification as an ongoing activity, you prevent a system from drifting into a state where it seems fine but is no longer trustworthy. Continuous verification becomes more intuitive when you connect it to the reality of change, because change is where security posture is most commonly lost. A system might start with clear requirements and a sound design. Then a small change is made to meet a deadline, and another change is made to integrate a partner, and suddenly the original security boundary assumptions no longer hold. Even if no one intends to weaken security, drift happens because complex systems behave like living things that adapt to pressure. Continuous verification counters drift by creating frequent moments where the system is compared to the security requirements, not just to functional expectations. For a beginner, it helps to see this as the security version of checking your route during a trip rather than only checking at the destination, because missing a turn early can place you far from where you intended to be. On the exam, scenarios about repeated incidents, inconsistent control behavior, or surprise audit failures often reveal drift caused by missing continuous verification. Recognizing drift quickly is a major advantage in choosing the best answer. The next concept to lock in is the relationship between security requirements and evidence, because continuous verification is really continuous evidence generation. Evidence can be many things at a high level, such as documented approvals, traceable design choices, test results that confirm behavior, and monitoring signals that show controls are operating in production. The important idea is that evidence must be tied back to specific requirements. Otherwise, it becomes noise that looks impressive but proves nothing. Beginners sometimes think evidence means having many documents, but evidence is stronger when it is direct and relevant, like a clear demonstration that unauthorized access is blocked or that critical actions are logged with identity and context. Continuous verification works best when evidence is produced as a natural byproduct of normal delivery and operations, because that makes it sustainable. If evidence requires heroic effort every time, it will be skipped under pressure, and then confidence becomes guesswork. Exam questions often reward answers that connect requirements to ongoing evidence rather than one-time checklists, because that shows an engineering mindset rather than a compliance theater mindset. To understand how continuous verification fits into modern delivery, it helps to define the software development lifecycle, SDLC, in a way that emphasizes flow instead of phases. The SDLC describes how software is conceived, designed, built, tested, deployed, operated, and changed, and security requirements should be present throughout that flow. In older mental models, verification might be imagined as a test phase near the end, but modern delivery often blurs phases because design and implementation evolve together and deployments happen frequently. Continuous verification means you verify security requirements at multiple points, using the type of evidence appropriate to each point. Early in the flow, verification may look like checking that requirements are complete, consistent, and testable, because unclear requirements cannot be verified later. During design, verification includes checking that architecture decisions satisfy the requirements, especially around trust boundaries and privilege. During implementation and deployment, verification includes checking that behavior matches intent and that changes did not quietly break earlier guarantees. A practical way to build this habit is to think of each security requirement as having an associated verification story, meaning you can describe how you will know the requirement is met, how often you will check it, and what would count as a failure. For example, a requirement about least privilege should have a verification story that includes how permissions are granted, how they are reviewed, and how exceptions are detected. A requirement about data protection should have a verification story that includes how data flows are identified, how protection is applied at storage and transit points, and how copies like logs or backups are controlled. A requirement about auditability should have a verification story that includes what events must be recorded, how identity is captured, and how log integrity and availability are maintained. Beginners often write requirements as statements that sound good, but without a verification story, the requirement is fragile because people will interpret it differently. Continuous verification is the practice of keeping those stories alive as the system changes. On the exam, a strong answer often includes strengthening the verification story rather than adding a random control. Modern delivery often includes practices such as continuous integration, CI, and continuous delivery, CD, and these concepts matter here because they change the tempo of change. When changes are integrated frequently, you cannot rely on occasional, large security reviews to catch problems, because the system may change again before the review is complete. Continuous verification aligns with CI and CD by embedding security checks into the same rhythm that moves work forward, so security becomes part of normal quality rather than a separate event. This does not mean every change triggers an enormous security evaluation. It means that the checks are scaled to the change and focused on what the requirements demand. For example, changes that affect authentication, authorization, or logging should trigger focused verification because those areas define trust and accountability. Changes that affect performance or availability should trigger verification related to resilience requirements. Beginners sometimes assume that faster delivery forces weaker security, but continuous verification is a key reason that is not necessarily true, because faster delivery can include faster feedback. The exam often tests whether you understand that security can be strengthened by frequent, disciplined checks instead of being weakened by speed. One beginner confusion that deserves attention is the difference between verifying requirements and verifying controls, because people sometimes verify that a control exists and assume that means the requirement is met. A control is a means, while a requirement is an end, and a control can exist while still failing to achieve the requirement due to misplacement, misconfiguration, or misunderstanding. For example, access control mechanisms can exist while still allowing overprivileged roles, which violates least privilege requirements. Logging systems can exist while still failing to capture the right events or the right context, which violates auditability requirements. Encryption can exist while keys are poorly managed, which undermines confidentiality requirements in practice. Continuous verification keeps attention on outcomes by repeatedly asking whether the requirement is actually satisfied in the current system state, not just whether a control is present. This mindset helps you avoid shallow answers that focus on installing more controls instead of confirming effectiveness. In exam scenarios where controls exist but incidents continue, The likely issue is effectiveness and verification, not the absence of any control at all. Another core idea is traceability, because continuous verification depends on knowing what to verify and why, especially as systems change. Traceability means you can connect a security requirement to the design decisions that support it, connect those decisions to what was implemented, and connect that to verification evidence and operational monitoring. When traceability is weak, verification becomes guesswork because reviewers do not know what changed, what requirement it impacts, or what evidence is needed to confirm continued compliance with intent. Beginners sometimes treat traceability as paperwork, but in security engineering it is how you preserve intent through change, much like a map preserves direction when you take detours. If a system evolves without traceability, a team may repeatedly verify the wrong things, missing the real risks introduced by new interfaces or new privilege paths. Continuous verification works best when it is guided by traceability, so checks follow what matters rather than what is convenient. On the exam, answers that strengthen traceability often represent the most defensible approach because they improve both security and delivery predictability. Continuous verification also relies on thinking in terms of risk and impact, because not every requirement needs the same frequency or depth of checking. A requirement tied to high-impact assets, such as sensitive records or critical system availability, should be verified more frequently and with stronger evidence because the cost of failure is high. A requirement tied to lower-impact features might be verified less frequently, but still consistently, because drift can accumulate quietly over time. This is where a mature approach avoids both extremes. It avoids ignoring verification until the end, and it avoids creating heavy processes that teams bypass. Beginners sometimes think continuous means constant, but continuous in engineering often means integrated into the normal flow, repeated at sensible intervals, and triggered by meaningful changes. When you align verification effort with risk, you protect what matters most while keeping delivery moving. Exam questions often include constraints like limited time or frequent releases, and risk-based verification is a realistic way to satisfy requirements without freezing progress. The best answer usually shows that you can prioritize verification based on what failure would mean for mission and trust. Operational monitoring is a major part of continuous verification because it provides evidence that controls are working after deployment, when real users and real conditions interact with the system. Many security requirements are not fully verified by pre-release testing alone because threats and misuse patterns appear in production, and systems can drift through configuration changes or dependency updates. Monitoring supports verification by providing signals such as access patterns, authentication anomalies, privilege changes, and unusual data movement, which can indicate whether requirements like least privilege and auditability remain effective. A beginner might think monitoring is just for incident response, but in security engineering it is also part of assurance because it continuously checks assumptions. If monitoring is weak, the organization may not notice that a control failed until damage occurs, and that makes verification reactive rather than continuous. Designing monitoring as evidence means choosing what to observe based on requirements, not just collecting everything and hoping it helps. Exam scenarios that mention uncertainty about security posture, incomplete logs, or repeated unnoticed changes often point toward insufficient monitoring as a verification gap. Recognizing monitoring as verification makes your reasoning more aligned with security engineering practice. Change control connects directly to continuous verification because every meaningful change is a moment when a requirement might stop being true. If a change alters an interface, adds a new dependency, modifies permissions, or changes how data is handled, the verification story must be revisited so confidence remains justified. This does not require an enormous process for every change, but it does require a disciplined habit of asking what requirements are impacted and what evidence must be refreshed. Beginners sometimes assume that security verification is separate from change processes, but in reality, the best verification opportunities are often triggered by change because change provides a natural checkpoint. Controlled change also supports verification by ensuring the system state is known and baselined, which makes evidence meaningful. If the environment is chaotic and undocumented, verification results quickly become outdated because nobody knows what is currently deployed. Continuous verification and change control reinforce each other. Change control prevents uncontrolled drift, and verification ensures controlled changes did not break security intent. On the exam, scenarios about configuration drift, repeated reintroduction of old issues, or inconsistent environments often indicate that change processes are not tied to requirement verification. It is also important to address the human misunderstanding that continuous verification is mainly a security team activity, because that belief creates bottlenecks and late surprises. In a healthy engineering environment, continuous verification is distributed, meaning developers, testers, and operators each play a role in producing evidence and checking requirements in their part of the lifecycle. Developers contribute by building features that include security behavior and by supporting testability through clear interfaces and predictable error handling. Testers contribute by validating requirement satisfaction through repeatable checks that focus on security behaviors, not just functional outcomes. Operators contribute by maintaining baselines, watching monitoring signals, and ensuring changes are controlled and observable. Security specialists contribute by defining requirements clearly, shaping verification stories, and focusing verification effort where risk is highest. Beginners sometimes imagine that security is enforced by a single gatekeeper team, but modern delivery works better when security verification is integrated into normal responsibilities. Exam questions that describe overloaded security reviewers or late-stage security failures often point toward missing shared ownership of verification. As you build comfort with continuous verification, it helps to internalize that verification is not only about catching failures, but also about building confidence that supports faster, safer delivery. When teams can verify security requirements quickly and consistently, they are less afraid of change because they have feedback that tells them whether security intent still holds. That feedback reduces the temptation to slow down delivery out of caution, and it reduces the temptation to rush changes without checking because the checking is built into the flow. Continuous verification also improves learning because it reveals patterns, such as which requirements are most often broken by changes, which interfaces cause the most misunderstandings, and which controls produce weak evidence. That information can be used to refine requirements, improve design patterns, and strengthen monitoring, creating a cycle of improvement. Beginners may worry that continuous verification adds overhead, but unmanaged uncertainty adds far more overhead through incidents, rework, and last-minute compliance crises. The exam often rewards this mindset because it shows you understand that security and delivery can reinforce each other through disciplined evidence and feedback. As we close, the key takeaway is that verifying security requirements continuously across the SDLC and modern delivery is a way of keeping security promises true as reality evolves. Verification means checking that requirements are satisfied, not merely that controls exist, and continuous verification means those checks repeat at sensible points, especially when meaningful changes occur. Evidence, traceability, risk-based prioritization, operational monitoring, and controlled change are the pillars that make continuous verification sustainable rather than exhausting. When you connect verification stories to requirements, you create clarity about what must be shown, how often it must be shown, and what failure would look like, which turns security into a discipline rather than a hope. Modern delivery practices like CI and CD make this even more important because they increase change tempo, and continuous verification provides the feedback that keeps confidence aligned with that tempo. If you can explain how continuous verification prevents drift, supports assurance, and enables predictable delivery, you will be thinking exactly the way ISSEP questions are designed to measure.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.